Shown is a graph of an electric potential as a function of position. This is a one-dimensional coordinate system. Suppose we have a one-dimensional coordinate system in which charges are constrained to move along the x-axis only. Well, what we have shown on the left is a graph of an electric potential as a function of this position. That electric potential looks something like this. And again, these charges are constrained to move only along the x-axis. But I'm going to draw the potential axis. So vertically corresponds to potential energy. Horizontally corresponds to the position of the particle or a position along an x-axis. Now our potential function looks something like this, where point B is right at the top of the hill there, and point A is right crossing through the middle. So for part A, the question is, if a positively charged particle is placed at point A, so here is our positively charged particle placed at point A, what will its subsequent motion be? In other words, what is it going to do? Well, remember, positive charge will accelerate from high potential to lower potential. Now, this is in the absence of any other fields or forces. All we're dealing with here is electric potential due to the electric field, which is a conservative vector field that would allow an electric force between a charge placed in the field. So if we want to know what the motion of this charge would be, well, since positive charges accelerate from high potential to lower potential, the charge would start accelerating in the negative x direction, because this would be the direction of that conservative force that causes it to accelerate from high potential to low potential. So since our charge starts off with a certain value, a certain positive value of electric potential, it'll accelerate to the left. When it gets in this region, as it gets to the bottom of this little valley, it'll slow down as it starts going back up until it reaches the origin, because now it's gaining electric potential. Now remember, electric potential is a measure of the ability of an electric field to give another charge electric potential energy. We know that the change of electric potential energy is equal to the product of the charge times the change of electric potential. And we know that from conservation of energy, the change of kinetic energy plus the change of potential energy in the absence of any other external forces is equal to 0. This means that as we lose potential energy, we gain kinetic energy. And as we gain kinetic energy, we lose potential energy. So for this proton, and I'm going to identify these different regions as region 1, region 2, region 3, region 4, and region 5. So the proton will speed up in region 3 because its potential energy is increasing, or decreasing rather, which means its kinetic energy is increasing in region 3. In region 2, it's at the bottom of that mini hill and starts going back up again, which means its electric potential is increasing, but positive charges will want to decrease their electric potential if possible. So since the electric potential is increasing, that comes at a cost of decreasing the kinetic energy of that proton in that region. But then now, once we cross the origin, the electric potential is decreasing again, which means the electric potential energy is decreasing, which means that the kinetic energy is increasing. So what will the motion of the proton be? It'll speed up, briefly slow down a little bit, and then continue to speed up as it accelerates from right to left. Now let's do the same thing for a negative charge. So we have regions 1, 2, 3, 4, and 5. And this time, however, the negative charge is placed right at the top of this hill. And the question is, if that negative charge is given a very small kick to the right, what will its subsequent motion be? So right now, before we do anything, the electric charge is just sitting there. It is right at the top of the hill. It is in equilibrium for all intents and purposes, but it's in unstable equilibrium. One, the electron let's remember that negative charges will accelerate from low potential to high potential. If we do nothing to this negative charge at the top of the hill at point B, it'll just sit there. It is at the highest possible value of potential it can be at. And it wants to be there because negative charges will accelerate from low potential to higher potential. And there is no higher on this curve. This is why we have to give this electron a little kick to unseat it from its equilibrium. We give it a little kick to the right, which gives it an initial velocity and also an initial kinetic energy. So right now, this horizontal line I'm drawing represents the total energy of the electron, a combination of So when we give that electron a kick to the right, it will start moving to the right. And as it starts moving to the right, and even though I have the electron drawn at the top of the hill, it's really down here on the x-axis. The hill just represents the value of electric potential. So as this electron moves to the right, it will slow down because it's moving from high potential to lower potential. This is because there is an electric force there's an electric force acting on the electron that tries to take it from low potential to high potential. So if we give this electron a kick to the right and it displaces to the right, then there will be an electric force that acts on it to the left. But then if that electron that we gave the kick to the right, that force will cause it to slow down, slow down, slow down, stop, and then it will cause it to speed up, speed up, speed up as it goes back to its equilibrium position. But now that it has some speed, it'll go to the other side, slow down, slow down, slow down, stop. And at that point, the reason why it's slowing down is because the electric force is trying to take it from low potential to high potential. So electric charges want to always accelerate from low to high potential. So it'll slow down as it crosses that line at point x equals b. It'll eventually stop at some point, and then it'll start accelerating, 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 crosses point B, slowing down, slowing down, slowing down, stop. And it'll continue oscillating on either side of that point B being the equilibrium position. And this is because the electron will accelerate from low to high potential, and depending on how much of a kick we gave it, determines whether or not the electron goes all the way out here before stopping and reversing direction, and it'll go an equal distance away from B, or not an equal distance rather, it'll go to a point away from B, eventually stop, and it'll oscillate on opposite sides of B.